Welcome, everyone. Today, we are exploring a critical topic for the future of technology: the carbon footprint and energy usage in computing, focusing specifically on data centers, resource costs, and the ongoing shift toward green compute. Here is a brief overview of our agenda. We will begin with an introduction to the physical costs of digital tech, examine data center energy and water consumption, look at carbon emissions driven by the AI boom, explore strategies for green compute, and conclude with a special addendum addressing the widespread myths surrounding space-based data centers. To most end users, cloud computing, AI models, and data storage feel entirely weightless. However, the underlying digital infrastructure demands massive physical resources, including gigawatts of continuous electricity, billions of gallons of water for cooling, and heavy carbon footprints tied to local power grids. This brings us to our core question: how do we scale computational intelligence without exhausting planetary resources? Modern hyperscale data centers consume as much power as small cities, scaling into tens or hundreds of megawatts. We measure facility efficiency using power usage effectiveness, or PUE, which is the ratio of total facility energy to IT equipment energy. While older legacy centers had a PUE around 2.0, meaning half their energy went strictly to overhead and cooling, modern hyperscale facilities approach 1.1 to 1.2. Unfortunately, these efficiency gains are constantly outpaced by the exponential growth in computing demand, particularly driven by large language models. This breakdown illustrates where power goes in a conventional data center facility. Roughly 60% of total grid power directly powers the IT equipment, such as compute servers and storage. Cooling systems account for about 35%, while power conversion and distribution losses make up the remaining 5%. Beyond electricity, data centers require constant thermal management to prevent hardware degradation. Direct water usage occurs through evaporative cooling towers that consume millions of gallons of municipal water daily. Indirect water usage represents the water consumed off-site by thermoelectric power plants, generating the server's electricity. A major challenge is that many data centers are located in arid regions, like the American Southwest, placing severe strain on local water tables. Carbon emissions are broken down into three scopes. Scope 1 covers direct on-site emissions from emergency diesel backup generators. Scope 2 covers indirect emissions from purchased electricity. Scope 3 encompasses supply chain and embodied carbon from hardware manufacturing, chip fabrication, and facility construction. The AI dilemma is stark. Training a single frontier large language model can emit hundreds of tons of carbon dioxide, equivalent to multiple transatlantic flights. Achieving sustainable computing requires a multi-pronged strategy. First is renewable energy matching, transitioning grids to run on 24/7 carbon-free energy like solar, wind, nuclear, or geothermal. Second is advanced thermal engineering, utilizing liquid immersion cooling instead of power-hungry air HVAC systems, alongside geographic load shifting to run workloads where green energy is active. Third is algorithmic efficiency, optimizing model architectures, pruning parameters, and using smaller specialized models instead of massive monolithic ones. This framework outlines how hardware optimization and clean energy sources feed directly into algorithmic efficiency. Together, these pillars form the foundation required to achieve sustainable, net zero computing ecosystems. Ultimately, the exponential growth of AI makes energy and water management an existential challenge for the tech sector. True sustainability demands a holistic approach combining transparent carbon and water accounting, ongoing efficiency innovations, and public grid modernization. Our ultimate goal must be completely decoupling digital growth from environmental degradation. Now let's look at an addendum addressing the recent trend of proposing space-based data centers. Proponents argue that moving compute to orbit or the moon leverages continuous solar power and the free cold of deep space. However, the physical reality is that space is deeply hostile to high-density silicon. The two major blockers are thermal management and power transmission constraints. On Earth, data centers rely heavily on air and liquid conduction and convection to shed heat. In the vacuum of space, those mechanisms do not exist, meaning heat can only escape via slow thermal infrared radiation. As a consequence, radiators must be gargantuan in surface area to shed kilowatts of heat, and direct sunlight causes extreme thermal swings from minus 150 to plus 120 degrees Celsius, rapidly degrading hardware. This contrast highlights the fundamental thermodynamic differences. Earth-based cooling benefits from active conduction, convection, and scalable liquid chillers to optimize PUE. Space-based cooling faces a total vacuum with zero convection, relying 100% on slow radiation and requiring massive radiator surface areas. Beyond thermal issues, power delivery via gigawatt-scale solar infrastructure in space is economically prohibitive to launch. There is also a massive communication bottleneck. Transmitting terabits of real-time AI inference data between Earth and orbit introduces severe latency and atmospheric interference. Furthermore, cosmic rays cause hardware bit flips, and there are no on-site technicians to fix failed hardware. Space compute remains fundamentally impractical. So why are tech billionaires pushing for this? It acts as a narrative compounder, marrying high-demand AI with futuristic space infrastructure to capture investor mindshare and lock in capital regardless of physical reality. This feeds a speculative bubble where multi-decades away sci-fi fantasies are priced into current stock valuations, driving systemic market overvaluation. As we build and scale the next generation of AI systems, the responsibility falls on us to ensure that technological progress does not outpace our planetary boundaries. Let's focus our innovation on efficient algorithms, smart green energy grids, and sustainable terrestrial infrastructure rather than chasing orbital distractions.